Welcome to your review for Physics Projectile Motion. First of all, let's think about a free body diagram for a projectile. A projectile you can just think of as anything that is thrown or launched. It could be a football flying through the air, it could be a bullet, it could be a rocket, it could be you if you are jumping and in the air. The free body diagram contains one and only one force on it, and that is the weight of the object. That is the attraction of that object with the Earth. We are going to ignore things like air resistance. We'll just keep the situations more simple. If the free body diagram contains one and only one force, which points down, then that means that the net force points down. The net force is in the down direction. Therefore, the acceleration vector must be down. The acceleration for any projectile, no matter how it is thrown or launched, has an acceleration vector that points down, and that value is g, little g, which is about negative 10 meters per second squared on Earth. We have a couple of situations that we're going to consider. First, let's think about the equations that we have available to us. We have one and only one equation in the horizontal direction, and that is delta x, the displacement in the horizontal direction, keeping horizontal and vertical completely separate, is equal to the horizontal velocity times the time. In the vertical direction, if we're considering the vertical motion, again, horizontal and vertical completely separately, I have four total equations that I can choose from. These are the four motion equations that we've been working with. We've just made them more specific for the vertical direction. So instead of saying v initial velocity, we would say initial velocity in the vertical direction. So v for velocity, y for which direction, the vertical direction, or along the y-axis, and then I for initial. So we have all four of those available, and then how we know which one to choose just depends on what we're given and what we're solving for, and usually, most importantly, what we don't know. If an equation has a variable that we don't know in it, then we can't use that equation. So let's take a look at where the initial velocity is pointing straight up. In other words, the object is thrown or launched upward. You take a tennis ball and throw it directly vertically. The initial velocity is vertical, but for projectiles, we will not discuss the velocity very often. What we will talk about is the horizontal velocity and the vertical velocity. In other words, how fast is it going in the horizontal direction and how fast is it going in the vertical direction. That's what we really want to know. So if you throw an object straight up, that means that the initial velocity in the vertical direction is, well, straight up. The horizontal velocity is 0. Because if you throw an object straight up, there is no horizontal component or part to that. The object is only moving vertically, has no horizontal part to its motion. The vertical velocity changes because of the influence of gravity, because there is acceleration in the vertical direction, but the horizontal velocity starts at 0, it stays at 0. In other words, if I throw a ball straight up, it doesn't suddenly start moving to the right. The horizontal velocity starts at 0 and it stays at 0. If I launch a projectile horizontally, this could be a ball rolling off of a horizontal table. This could be a bullet that is fired exactly horizontally. It could be a ball that is thrown with a perfectly horizontal initial velocity. Then the parts that I care about are, what is the initial velocity in the vertical direction? Well, it's 0, because if it's horizontal to start with, there is no vertical component or part to horizontal. Horizontal and vertical are separate from each other. But that changes. The vertical velocity may start at 0, but it won't stay at 0. As soon as the object is under the influence of gravity, it will change its vertical velocity because of the influence of gravity. The horizontal velocity starts to the right and, again, is constant. The reason that we know that the horizontal velocity is constant is because there is no force in the horizontal direction. I can't change a horizontal velocity without a horizontal net force, and I don't have one. I don't have any forces in the horizontal direction. Therefore, there's no net force in the horizontal direction. Therefore, there's no acceleration in the horizontal direction, and that horizontal velocity just stays whatever it was from the beginning of the problem. Now, the last option is you launch your object at an angle. Now, this is the case where you will have both a vertical and a horizontal component. If the object is thrown or launched up and to the right, then the initial vertical velocity is up. That is the up component of that velocity, but it will change. Vertical velocity is always changing. And the horizontal velocity is to the right. If you throw the object up and to the right, it has an upness to it, that's Vyi, and a rightness to it, Vx. And once again, Vx is constant. So look at what we see here for those three options for how you can launch a projectile. We see that the vertical velocity, the vertical component or part of the velocity always changes because of the influence of gravity. I have acceleration in the vertical direction. In the horizontal direction, though, it remains constant. This is just a free body diagram for something that is thrown upward. We could see that our velocity vectors are changing. And on the way up and on the way down, the acceleration still points down. If I launch an object horizontally, then I end up with my motion diagrams that look something like that. And the acceleration is still down. You can get that from two ways, knowing the direction of acceleration. One is, what would I have to do to V1 to turn it into V2? I would have to take the handle of V1, the earlier vector, and drag it down to make it change direction. That'll work. You can also go with, look at your free body diagram. Free body diagram has one vector that points down, net force down, acceleration down. Make sure you've thought through the difference between which way the object's going, that's velocity, and acceleration, which describes how that velocity changes. Acceleration is not which way the object is traveling. If I launch at an angle, then I get something that looks like a rainbow or a parabola. In that case, vertical velocity changes, horizontal velocity stays constant, and the acceleration is, once again, down. Very important that you know that the acceleration vector for projectiles points down. You can see these horizontal components of the velocity stay constant. That's what those green vectors are showing. Whereas the vertical vectors are changing length. Those are the Vy's. Those are changing because of the influence of gravity. Let's look at a sample problem. So we have a table, it's 0.60 meters high. You just roll a billiard ball off of the edge of the table, and it rolls off with a horizontal velocity of 2.4 meters per second. We'd like to know how long it's going to take to hit the ground and where it hits. So first task, really for any problem, will be to draw a picture. If there's not already a picture drawn, draw one. This helps you visualize the situation. So I have equally spaced, so the red dot indicates the billiard ball right when it leaves the edge of the table. Horizontally, I've drawn equally spaced red dashes. That shows where the object has traveled in the x direction, and in the vertical direction, they are not equally spaced. They're getting farther and farther apart in the vertical direction. And then to put the dots, I'm just going to kind of connect those grid lines. And then that'll show me what, basically the path. That'd be a half a parabola. And then I set up the variables, possible variables in the x direction, and start filling those in. So let's see what we know. We know that x0 is 0. That's just because I get to choose where the origin is. I would choose the origin as the base of the table. T0 is 0 because I'm going to start the clock at 0. Vx is 2.4 meters per second because we are told that it leaves the table with a horizontal velocity of 2.4 meters per second. That means that it also is traveling 2.4 meters per second in the split second before it hits the ground. We never consider our final velocity to be after it hits the ground because it's not a projectile once it hits the ground. We're only ever going to consider our beginning and ending set of information as the moment it leaves the table until the moment right before it hits the ground. So it is still traveling 2.4 meters per second 2.4 meters every second that it is in the air. That means the acceleration in the horizontal direction is 0. It's because I have no net force in the horizontal direction to cause that velocity to change. I don't know anything about positions or times. But now so I know I want to know delta x, I want to know how far it lands, I want to know delta t, I want to know how long it's in the air. In order to find that, I'm going to use vertical information. So I set up my possible variables in the vertical direction and then fill in what we know. So it's the thing with projectiles is you have to organize the horizontal information and the vertical information. So y0 is 0.6 meters because I chose the origin as the base of the table, so it starts off 0.6 meters above the table. y1 is 0. Technically, it's ever so slightly above 0 meters, but it's so close that we can just treat that as 0. Again, we don't consider after it hits the ground, but the split second before it touches the ground. T0 is 0, don't know the final time. I do know delta y, which is negative. Negative because it travels down, and also because final minus initial would be 0 minus 0.60. Vyi is 0 because it doesn't have any vertical velocity at the moment that it leaves the table. It doesn't start moving in the vertical direction until some amount of time has gone by. And I do not know Vy final. I can't say that Vy final is 0 because it hit the ground, because again, Vy final would be how fast is it going right before it hits the ground. And I always know acceleration in the vertical direction is g is negative 10, because I'm getting ready to use those in motion equations. G is negative 10 in a motion equation. It's only positive 10 if I'm calculating the weight of an object. Okay, so I want to know delta x, and the one and only equation that has delta x in it is delta x equals vx times t. So I look at my known information. I know vx, that's great, but I don't know t. I would be stuck if I didn't have all that vertical information. So now let's go use the vertical information to find t. And the way I choose this equation is I say, I know delta y, I know g, I know vyi, and I don't know vyf. The fact that I don't know vyf dictates this equation. This is the only equation that doesn't have the final vertical velocity in it. So I have to choose that one. I put in my numbers, which is easy now that I've done all that thinking up above. 0 times anything is 0, so I get t squared by itself, and then take the square root. Once I know the delta t, then I can go back and put it in the horizontal equation in order to figure out how far it travels. Rule of thumb is that the time in the air is dictated by vertical information. That's what's going to determine how long an object is in the air, is how high it is above the ground. And the vertical information dictates time. And so you get that you would have traveled 8.6 meters horizontally. It lands 8.6 meters from the base of the table. Let's try another problem. Now, this time we have an object that's going to be launched at an angle. So this is a long jumper, leaves the ground, and we know how fast, and we know the angle. Anytime we have any vector at an angle, the first thing we're going to do is break it into components. So we want to know several things here. We want to know the time of flight, the horizontal distance traveled, that would be important if you're a long jumper, and how high, the peak height. So first thing, let's kind of picture what would happen. Get launched into the air, travel up, travel back down. Mental picture. It's kind of a simple motion diagram. Let's start organizing our information here. Just horizontal first, x0, t0, and vx. And now we have to decide what our next interesting point is. And we have two options. The interesting points could be the highest point, or it could be the long jumper right before she hits the ground. I chose the highest point because I was asked about the peak height. So the peak height will happen when the long jumper is up at the highest point. And we know that at the highest point is a turnaround point, and so that means that the velocity in the y direction will be 0 up there, so that'll make that point easy. So if I can find the time that it takes to get up to the highest point, then because this motion is symmetrical, the time up equals the time down. So the time it takes to get to the highest point times 2 would give you the time of flight. Now, you could just as easily have chosen your second interesting point to be the long jumper right before she hits the ground. In that case, you would say that delta y was 0. She starts and ends at the same height, and calculate the time. Either way would work just fine. Just practice enough to sort out which one you like better. Okay, so let's figure out what we have here. We have this vector that is an angle, 12 meters per second, an angle of 28. So 12 meters per second is dictated by how fast she can jump off the ground. We're first going to break that into the horizontal and vertical components. Horizontal would be the hypotenuse, which is the actual velocity, times cosine of the angle. That gives us 10.6 meters per second. Make sure you're in degrees. Vyi would be the initial velocity times the sine of the angle. That gives us 5.6 meters per second. So once I've done that, the number 12 will not appear in any of my equations. The number 12 itself does not appear in the horizontal or the vertical equations. All right, so we're going to say that she starts at 0 height, time is 0, and we put in our initial velocities for both of those. Again, the number 12 does not appear in there, just the horizontal and the vertical components. All right, we don't know how far she is. We do know that in the horizontal direction, though, she continues to go 10.6 meters per second the whole time. At the top of the path, we don't know how high she is, and we don't know how much time that takes, but we do know that her vertical velocity will be 0 at the top of the path. Not her overall velocity, because she's got that horizontal 10.6 the whole time. So she is not stopped at the top of the path. It's just her vertical velocity is 0 at the top of the path. And identifying what the deltas are. I don't know delta x, I don't know delta t. I always know ax is 0 because no force. Delta y, don't know. Delta t, don't know. We always know ay. So let's figure out the time of flight first. So our approach here is we're going to say the time to the top of the path, the total time is twice the time that it takes her to get to the highest point. So let's just find that highest point. The time to get to the highest point would be given by VYF equals VYI plus GT. So VYF would be her velocity at the top of the path, which is 0. Initial velocity was 5.6, negative 10 for acceleration due to gravity. How much time would that take? 0.56 seconds to get up to the top of the path. Therefore, the total time of travel, 0.56 up, 0.56 down, gives you 1.12 seconds. Her horizontal distance traveled is going to be a delta x. Make sure you have your list of variables in units. Delta x equals vxt. That is your only choice for an equation in the horizontal direction. She's traveling 10.6 meters per second for a total of 1.12 seconds. That means that she must have gone 11.9 meters. Maximum height, so now I already know my time for maximum height. Vf squared equals Vi squared plus 2g delta y. At the top of the path, she's going 0 in the vertical direction. Initial in the vertical direction is 5.6. 2 times negative 10 times delta y. That's going to give me delta y between the ground when she was at 0 and the top of the path. So delta y would equal 1.6 meters. You'd have to do 0 squared is 0, 5.6 squared, find that number, subtract it to the other side, so you're isolating the term with the variable. So you end up with negative of 5.6 squared and divide that by negative 20, and that'll give you 1.6 meters. You'll never have to do any kind of artificial going back and fixing the sign of things. Delta y is positive mathematically, and that's what we would expect. She does travel up as she gets to the top of the path. So 1.6 meters is how high she gets above the ground. Okay, so key principles here is you always know that ax is 0, the acceleration in the horizontal direction is 0. You always know that ay, the acceleration in the vertical direction, is the acceleration due to gravity, or negative 10 meters per second squared. If your object is launched at an angle, first find vx, find vyi, and then sort out your variables, figure out what you need to solve for, and go from there. Good luck.